thousands of inputs. So immediately that becomes a complex architecture. So remember this concept or this term architecture. It's how the nodes are connected together. The inputs leading to the hidden layer, leading to the outputs. That is called architecture. So a deep learning architecture has a complex architecture. A deep learning model is more complex than a simple machine learning model. So I'll give you some examples of deep learning to illustrate this. So a machine learning model that uses just 5 proteins to predict cancer it's going to be just a machine learning model. It's not that deep. A deep learning model would use the whole proteome, or as much of the proteome that can be measured. That can be 4,000 proteins. That will be a deep learning model. A deep learning model could use image data based upon an array of pixels and their RGB intensities to predict the presence of cancer in a pathology slide. That would be a deep learning model because it uses a matrix of maybe 2,000 by 2,000 pixels. So again, that's got to be a deep learning model because of the complexity of the data. So you see what I mean. The concept's relatively simple. Large complex networks are deep learning networks. Smaller networks are just machine learning. So essentially this is a deep learning architecture. This is just a shallow machine learning architecture. But with deep learning, we can add more functionality into our network. We can add more layers. So a shallow learning or normal machine learning algorithm might have 2, 3, 4, 5 layers max. A deep learning model could have 50 to 200 layers in it. And we can add layers into them. So what I showed you with Deep Learning 4J in Weka, you can add layers in. So you build up the architecture of your machine learning by adding layers. You can add an input layer, you can add a convolutional layer, you can add a pooling layer, you can add a recurrent layer. So you add layers in to add functionality. And those layers have this sort of functionality. So an input layer is always going to just represent the information that you're feeding in. It could be an array of pixels, it could be a mass spectrum, it could be expression array data, it could be protein array data. It's a matrix of input values. A convolutional layer, and I'll go into this in a bit more in a second, essentially takes data from the input layer and represents shapes in data. So an image, you can imagine, is a 2D array. And in that 2D array, there are going to be lines. There are going to be lines which are horizontal, vertical, diagonal, both ways. And those lines make up shapes. So what a convolutional layer is doing is essentially working its way through a matrix of RGB values, a matrix of pixels, looking for shapes, and then encoding them into the neural network. So in machine learning, we have this concept called an encoder and a decoder. And the functional layers of a deep neural network are encoder layers. They're encoding for structures in the data to try and find patterns in those structures. Obviously, if we just put single pixels in as a long, thin strip of data, there wouldn't be any association of those pixels in an image. Because you know what you're looking for is the interrelatedness of the pixels and how they exist in space. Whereas sometimes you don't need a deep neural network for proteomics data because in the first instance you're just enriching. You don't need to know if those proteins are associating with one another. You just need to represent them in the matrix to see if they're associated with a question. So we use convolutional neural networks for structures within data, but we wouldn't use them if there's no immediate structure that we're trying to find. We might just want to find, in the first instance, associations. A lot of people have tried to use convolutional neural networks for proteomic and transcriptomic data. The problem there is the false discovery rate around that is massive, because the number of potential interactions in the data that could be distant, that can't be detected by convolutional layers, but could be very real, is massive. So the data is not structured in the right way to use convolutional layers. I hate to say it, but it's usually computer scientists who don't know how biology works that put biological data into convolutional neural networks. So we have pooling layers. They merge nodes to try and reduce the dimensionality. So, if you've got a 20 megapixel image, the dimensionality of that's massive. You want to cut that down and to simplify it. We can do time series analysis. So we would use time series analysis for things like predicting trends in things. If you wanted to play the stock market or work out whether Bitcoin was going to rise or drop in the next 6 months or week, then you could use that. But you can also use recurrent neural networks for language processing, because language is a series of events. The words I am using are in a series. So if I say, the cat sat on the mat, then it's forming word associations in a time series. And by using a time-based neural network, like a recurrent neural network or an LSTM, we can start to model structures in language as well, to look at how words are in a particular series. So ChatGPT and things like Alexa even are using a series or effectively a time series analysis with a deep neural network. Things like self-driving cars and Teslas which drive around, they are using convolutional neural networks, but they're using effectively 4D convolutional neural networks, because they have a spatial element, but they also have a temporal element as well. So you can do a convolutional neural network in one dimension straight line, 2 dimensions of straight line, a matrix, which is an image, that's 2 dimensions, or 3 dimensions, which is spatial resolution, or 4 dimensions, which is time as well. So you can predict from video or layers of video whether something's going to happen or not. Then we have fully connected layers. Shallow learning uses fully connected layers, or machine learning uses fully connected layers. Deep learning uses fully connected layers. Whereas a convolutional network or a time series analysis neural network is an encoder, the deep fully connected layers are the decoder part. They're decoding patterns in that input data. So you have an encoder decoder, and that's how the algorithm works. You encode information in your data, you decode the information to try and find patterns in that encoded data. And then that fully connected layer links to an output layer, and that can represent answers to questions. It can even have multiple outputs. You could have 20 output nodes, each one representing the probability of something. The future of medicine, I'll talk about that probably tomorrow or the day after. You can imagine a situation where you take a real-time proteomic profile of the serum sample of an individual from a worn device. That feeds a signal through to an algorithm, which immediately makes a prediction of whether you are having increased risk of 20 different diseases instantaneously in real time from a one device. That's the future of medicine. But you could encode that. The challenge, as with all machine learning, is getting the data to do that and getting the device to do that. But if you have the data, you can make the algorithm. So an input layer, I'll just go into these in some more detail. I'm not going to have time for the full lecture today, but I'm going to start getting some of the concepts across. So an input layer is the interface with the world. As your neural networks, you have an input layer of your eyes, your ears, your skin, your nose, your mouth. They are your input nodes, effectively. With all of those, your neural network interacts with the world. And each input node represents a feature. So it could be a pixel, it could be a protein, it could be a gene, it could be a part of a signal, a channel in the signal. It's a way of representing the world. And it is a variable. So each time point or each feature is varying through a population. Now we can transform or scale those values. What we often do is scale them to between 0 and 1 or between -1 and +1. I talked a bit about this yesterday. The reason we do that is because different things have different ranges. If we looked at 20 scientific measurements, they would all have different units. Some of those things would have very large units, and some of those things would have very small ranges of units. So by scaling them, we're taking away the unit variability effect size, effectively just looking at the patterns in those inputs. We will decode them later, but for the purpose of learning and patterns, we scale them. Now, this is going to be a little bit intense, but I'm going to go through it slowly, and I might stop at the end of this so you can think about it overnight. But how do convolutional layers work? So, this is an encoder layer, and what they do is they tend to look for patterns and structures in a matrix of inputs. So let's imagine a grid. Each grid has got a pixel in it, and that pixel has an intensity. We've got a big smiley face in the big center of that grid. Everything else is just plain white space. How do we represent that smiley face in that grid so that a neural network can say, this is a smiley face? Yeah? But to do that, we have to encode that smiley face within that matrix. And we encode that with a convolutional neural network. So basically it pre-processes matrices. This matrix can be one-dimensional, so it's effectively a line, two-dimensional, an x by y, three-dimensional, a 3D space. One way, by the way, just as a note, one way of doing drug discovery is you take a three-dimensional structure of a molecule and you represent that within the 3D convolutional neural network. And you can use that to see whether it will dock into a protein, which you also have a 3D convolutional structure for. So that's how some machine learning based docking works. So you can imagine you've got a cube, and in that cube you have a hydrogen here, you have an oxygen here, you have a nitrogen here, you have a carbon, 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 hydrogen, oxygen, carbon ring, and it's spatially located within that cube. So you're representing the 3D structure of the molecule within a cube, and then encoding that 3D structure with a 3D convolutional neural network. So it's encoding. The key point here is it's encoding that structure. In an image context, this is encoding shapes within the image. So what is convolution? And this is, sorry, where we get a little bit mathematical, but convolution is essentially matrix multiplication. So all of you who were at school did maths, where you look, multiply this 2 by 2 grid by this 3 by 3 grid. And this is where where biologists usually groan. But matrix multiplication is the base of convolution. You're processing a grid or matrix with another matrix. So let's say matrix xi is multiplied by a kernel, which is another matrix. What does that look like? Well, this is I'll keep it in the first instance simple. So we have a matrix of numbers, x1, 2, 3, 4, 5, 6 to I, x to xi. Yep, so that's just basically a one-dimensional matrix. And what we do is we want to multiply that by a kernel, k1, k2, ki. So basically we set off and start with our first position. And so x1 is multiplied by k1 and added, x2 is multiplied by k2 and added, x3 is multiplied by k3 and added. And we get an output from that called y1. So we're processing the first 3 bits of the matrix with this matrix, summing the values and putting them out to a number. So we have now processed that first part of the convolutional matrix, and we have that output, which is encoding it. What we then do is we then move along one. So then x2 multiplies by k1 goes to y2, x3 multiplies by k2 goes to y2, x4 multiplies by ki goes to y2. So we're shifting it along along the matrix. And each time we process the maths to produce an output. And that output is an encoded version of the array. Now we can put different functions in here. We can use effectively +1 multiplied by +1 multiplied by -1. We can take averaging if we want to smooth out values. But basically we can mathematically change that kernel to do different things. I'll show you some kernels in a bit. So if we were to process this, we have something called padding, which is the beginning part of the matrix, because that's not been processed through the whole kernel. But you see, if we apply this, the starting point is 0. We'll add some of these. So 0 times -1 is 0. 0 times 1 is 0. 0 times -1 is 0. Sorry, that's wrong. That should be a 0. The next one, oh no, we ignore the padding. The next one is 0 times -1 is 0. 0 times 1 is 0. 1 times -1, that's 1 times -1 is -1. But this has taken the +1 bias on it. That's why sorry, I'm getting confusing myself. There's a bias of +1. That's what I forgot to add. That's why it didn't work. So 0 times -1 is 0. 0 times 1 is 0. 0 times -1 is 0. Plus a bias of +1 makes 1. Okay? We move along one. 0 times -1 is 0. 0 times -1. So 0 times 1 is 0. 1 times -1 is -1. We add a bias of +1. We get 0. So it's like going along, processing as it goes along. And so the output of this, effectively, is this encoded array, which is the input applied to the matrix. So the next step, let's look at 2D. It gets more complicated, but effectively, to just illustrate how it works, we have, let's say, a 3 by 3 kernel. with a functional with numbers in it. We apply this grid to that matrix, and the summed value gives us here -8. Yep. We then move that along one and calculate the value. Move that along one more, calculate the value. Move it along one more, calculate the value. Move it along one more, calculate the value. Move it along one more, and calculate the value. So that will fill these 5 squares here. We then move it down one and move it along. Move it down one, along. So we're basically traversing the bigger matrix using that smaller matrix, making it move through and transforming the values. So that output matrix here is going to be used as an encoded layer in our convolutional neural network. Now, our kernels can be various sizes. We can have a 3x3, a 4x4, a 5x5. The bigger the kernel, the longer it'll take, but potentially the more detailed and accurate the encoding we get. Because if we can represent trends over bigger areas if we use a bigger kernel. What sort of kernels can we use? Well, if we look at these, this is a box blur. So this just takes everything multiplied by 1, but then divides by 9. So that's effectively averaging across that matrix. The matrix goes to a single point. It's in effect lowers the resolution and blurs the image. That might be just a way if you want to just kind of remove noise. There might be single pixels that by using that are causing problems. You would remove those by taking that blur. You can do the same thing. That's called a Gaussian blur. You're kind of biasing it a little bit more by using a different value, and the numbers are different. This one is called a Sobel edge detection. Sobel edge detection is used to determine edges, and it works to some extent to find horizontal and vertical edges. But for encoding, sometimes you want to represent shapes, and to represent shapes, you want to detect edges. So in your smiley face, there were going to be edges around the circle, and maybe edges around the eyes and the smile. You want to detect those edges as shapes. So that's the simplest possible form of doing that. So you're using one matrix to detect edges. But you can add all applied to the matrix in parallel. So you could have layer 1, which is a horizontal line detector. So that's reinforcing horizontal lines. Everything else is played down. You have a vertical line detection. You have a diagonal line detection and an opposite diagonal line detection. So each one of those is basically 4 kernels that are applied to 4 parts of the matrix separately but in parallel. And then you combine those into one set of results, which represent an increase in the size of the matrix but different line states. You could pool them as well if you wanted to. So what this is doing is going through images, detecting things and encoding things. Just to illustrate what the layer output looks like, this is what a convolutional output without going through processing of something might look like. So each pixel has effectively detected a different edge. Some of them horizontal, some of them are just transitions, some of them vertical, some of them diagonal. Here we've got circular lines, arcs, angles. These have essentially been encoded into the convolutional layer of the neural network. And that information can be used in a classifier. So, any questions around convolutional neural networks? it's a whole subject. You could probably do a degree in convolutional neural networks. There's that many things to consider, and it takes, they get very complicated. As I say, it can be in 200 layers. And strategies are there that will cope with that much information. So the next layer is pooling layers. How are we doing for time? A pooling layer merges multiple layers to simplify the network. We could end up by having a matrix of 20,000 by 20,000 features. A pooling layer basically cuts that down by summing or averaging. You could take one way of doing it is you work across the matrix. So you work your way through. You're looking at a 9 by 9 grid. You just take the max in the 9 by 9 grid for that. Max for the next one, max for the next one. So you have a smaller array of max values, but you don't overlap. You just literally go through the grid. So you take your first 9, you move along 3, and take the second 9. You move along 3, take the third 9. So by doing that, you're pooling, but it's not a rolling pool. It's literally summing those 9 pixels up, but they're not without overlap. I think probably I'm not going to go into time series neural networks today, but have a look at convolutional neural networks. Have a look at the basis behind them. It's quite a complex topic. Again, most people use them without fully understanding how they work. They have the broad principles, but if you ask them to derive a convolutional neural network mathematically, they would be very stuck. And so having an understanding of what they're used for, having an understanding broadly of how they work, is an advantage. Any questions? No? The convolutional neural networks piece is a bit of a simplification. It is a complex topic, but hopefully gives you a flavour of how they work. Okay, thank you very much.